This video is about the exponent rules, rules that govern expressions like 2 to the fifth or x to the n. 2 to the fifth is just shorthand for 2 times 2 times 2 times 2 times 2, written 5 times. And similarly, x to the n is just x multiplied by itself n times. When we write these expressions, the number on the bottom that's being multiplied by itself is called the base. And the number at the top, telling us how many times we're multiplying the base by itself, is called the exponent. Sometimes the exponent is also called the power. The product rule says that if I have x to the power of n times x to the power of m, that's the same thing as x to the n plus m power. In other words, when I multiply two expressions with the same base, then I can add their exponents. For example, if I have 2 cubed times 2 to the fourth, that's equal to 2 to the seventh. And that makes sense because 2 cubed times 2 to the fourth means I multiply 2 by itself 3 times, and then I multiply that by 2 multiplied by itself 4 times, and in the end I have 2 multiplied by itself 7 times, which is 2 to the seventh. I'm just adding up the number of times it's multiplied in each piece to get the number of times it's multiplied total. The quotient rule says that if I have x to the n power divided by x to the m power, that's equal to x to the n minus m power. In other words, if I divide two expressions with the same base, then I can subtract their exponents. For example, 3 to the sixth divided by 3 squared is going to be 3 to the 6 minus 2, or 3 to the fourth. And this makes sense because 3 to the sixth means I multiply 3 by itself 6 times, and then I divide that by 3 multiplied by itself twice. So when I cancel out 3's, I have 4 3's left. Notice that I have to subtract the number of 3's on the bottom from the number of 3's at the top to get my number of 3's remaining. That's why I subtract my exponents. The power rule tells us if I have x to the n power raised to the m power, that's the same thing as x to the n times m power. In other words, when I raise a power to a power, I get to multiply the exponents. For example, 5 to the fourth cubed is equal to 5 to the 4 times 3, or 5 to the 12th. And this makes sense because 5 to the fourth cubed can be thought of as 5 to the fourth times 5 to the fourth times 5 to the fourth. Expanding this out some more, that's 5 times 5 times 5 times 5 times the same thing times the same thing again. So I have 3 groups of 4 5's, which is a total of 3 times 4, or 12 5's. The next rule involves what happens when I raise a number or a variable to the 0th power. It turns out that anything to the 0th power is equal to 1. Usually this is just taken as a definition, but here's why it makes sense to me. If you have something like 2 cubed divided by 2 cubed, well, certainly that has to equal 1. Anything divided by itself is just 1. But using the quotient rule, we know that this is the same thing as 2 to the 3 minus 3, because when we divide two things with the same base, we get to subtract their exponents. Therefore, this is the same thing as 2 to the 0. So 2 to the 0 has to equal 1 in order to make it work with the quotient rule. And the same argument shows that anything to the 0 power has to be equal to 1. What happens when we take something to a negative power? X to the n is equal to 1 over x to the n. Again, most people just take this as a definition of a negative exponent, but here's why it makes sense. If I take something like 5 to the 7th times 5 to the negative 7th, then by the product rule, this has to equal 5 to the 7 plus negative 7, which is 5 to the 0, and we just said that that is equal to 1. Now I have the equation 5 to the 7th times 5 to the negative 7th equals 1. If I divide both sides by 5 to the 7th, I get that 5 to the negative 7th has to equal 1 over 5 to the 7th. So that's where this rule about negative exponents comes from. It has to be true in order to be consistent with the product rule. Finally, let's look at fractional exponents. What does an expression like x to the 1 over n really mean? Well, it means the nth root of x. For example, 64 to the 1/3 power means the cube root of 64, which happens to be 4. And 9 to the 1/2 means the square root of 9, which is usually written without that little superscript up there. Now the square root of 9 is just 3. Fractional exponents also make sense. For example, if I have 5 to the 1/3 and I cube that, then by the power rule, that's equal to 5 to the 1/3 times 3, which is just 5 to the 1, or 5. So in other words, 5 to the 1/3 is the number that when you cube it, you get 5. And that's exactly what's meant by the cube root of 5. The cube root of 5 is also a number that when you cube it, you get 5. The next rule tells us we can distribute an exponent over a product. In other words, if we have a product, x times y, all raised to the nth power, that's equal to x to the n times y to the n. For example, 5 times 7, all raised to the 3rd power, is equal to 5 cubed times 7 cubed. And this makes sense, because 5 times 7, all raised to the cube power, can be expanded as 5 times 7 times 5 times 7 times 5 times 7. But if I rearrange the order of multiplication, this is the same thing as 5 times 5 times 5 times 7 times 7 times 7, or 5 cubed times 7 cubed. Similarly, we could distribute an exponent over a quotient. If we have the quotient x over y, all raised to the n power, that's the same as x to the n over y to the n. For example, 2/7 raised to the 5th power is the same thing as 2 to the 5th over 7 to the 5th. This makes sense because 2/7 to the 5th can be expanded as 2/7 multiplied by itself 5 times, which can be rewritten as 2 multiplied by itself 5 times divided by 7 multiplied by itself 5 times. And that's 2 to the 5th over 7 to the 5th as wanted. We've seen that we can distribute an exponent over multiplication and division. But be careful, because we cannot distribute an exponent over addition or subtraction. For example, a plus b to the n is not generally equal to a to the n plus b to the n. A minus b to the n is not generally equal to a to the n minus b to the n. And if you're not sure, just try an example with numbers. For example, 2 plus 3 squared is not the same thing as 2 squared plus 3 squared. And 2 minus 3 squared is definitely not equal to 2 squared minus 3 squared. In this video, I gave 8 exponent rules, which I'll list again here. There's the product rule, the quotient rule, the power rule, the zero exponent, the negative exponent, the fractional exponent, and they're the 2 rules involving distributing exponents across multiplication and division. In another video, I'll use these exponent rules to rewrite and simplify expressions involving exponents. In this video, I'll work out some examples of simplifying expressions using exponent rules. I'll start by reviewing the exponent rules. The product rule says that when you multiply two expressions with the same base, you add the exponents. The quotient rule says that when you divide two expressions with the same base, you subtract the exponents. The power rule says that when you take a power to a power, you multiply the exponents. The power of zero rule says that anything to the zero power is 1 as long as the base is not 0. Since 0 to the 0 is undefined, it doesn't make sense. Negative exponents. To evaluate x to the minus n, we take the reciprocal 1 over x to the n. To evaluate a fractional exponent, like x to the 1 over n, we take the nth root of x. We can distribute an exponent over a product. A times b to the n is equal to a to the n times b to the n. And we can distribute an exponent over a quotient. A over b to the n is a to the n over b to the n. In the rest of this video, we'll use these exponent rules to simplify expressions. For our first example, we want to simplify 3 times x to the minus 2 divided by x to the 4th. There are several possible ways to proceed. For example, we could use the negative exponent rule to write x to the minus 2 as 1 over x squared. All that gets divided by x to the 4th still. Notice that we only take the reciprocal of the x squared. The 3 stays where it is, and that's because the exponent of negative 2 only applies to the x, not to the 3. Now, if we think of 3 as 3 over 1, we have a product of two fractions in our numerator, and so we evaluate that by taking the product of the numerators times the product of the denominators, which is 3 over x squared, all divided by x to the 4th. I can think of x to the 4th as x to the 4th over 1, so now I have a fraction over a fraction, which I can evaluate by multiplying by the reciprocal. That simplifies to 3 times 1 divided by x squared times x to the 4th, which is 3 over x to the 6th, using the product rule, since x squared times x to the 4th is equal to x to the 2 plus 4, or x to the 6th. An alternate way of solving this problem is to start by using the quotient rule. I can rewrite this as 3 times x to the minus 2 over x to the 4th, and by the quotient rule, that's 3 times x to the minus 2 minus 4, or 3 times x to the minus 6. Now using the negative exponent rule, x to the minus 6 is 1 over x to the 6th, and this product of fractions simplifies to 3 over x to the 6th. The same answer I got before. The second problem can be solved in similar ways. Please pause the video and try it before going on. One way to simplify would be to use the negative exponent rule first and rewrite y to the minus 5 as 1 over y to the 5th. Thinking of this as a fraction divided by a fraction, I can multiply by the reciprocal and get 4y cubed y to the 5th over 1. By the product rule, the numerator here is 4y to the 8th, and so my final answer is just 4y to the 8th. Alternatively, I could decide to use the quotient rule first. As in the previous problem, I can write this as 4y cubed minus negative 5 by the quotient rule, and so that's 4y to the 8th, as before. I'd like to show you one more method to solve these two problems, kind of a shortcut method, before we